In this video, we're going to check out a couple of wireless standards that offer us bandwidth like we've never seen before in wireless technologies. In fact, these technologies, they often run faster than our high-speed wired LANs, which might be running at a gigabit per second. These two technologies are 5G and Wi-Fi 6, where 5G is a cellular data service and Wi-Fi 6 is a wireless LAN standard. First, let's consider 5G, which stands for the fifth generation of cellular technology. Cellular data speeds were able to take huge leaps with 5G because 5G uses an entirely different band of radio frequencies, and they're much higher frequencies than frequencies used by 3G and 4G. Specifically, the theoretical maximum throughput of a 5G connection is 20 gigabits per second. Of course, that's the theoretical maximum, but what can you and I expect? Well, Qualcomm says that a typical wireless user will get a 5G throughput on the order of 1.5 gigabits per second. Still, that's way beyond what we've typically had on our wireless LANs. Now, what makes that possible is that different band of frequencies that we mentioned earlier. With 5G, we use very high frequency, typically in the range from 30 through 300 gigahertz. Now that means that wavelengths of one of these radio waves is very small, on the order of millimeters. And these higher frequencies, they allow us to squeeze more data into a transmission. The challenge with that is those high frequencies, they get absorbed by walls and windows and lots of other material, much more so than frequencies used by 4G. For example, have you ever seen the submarine movie where a sub needs to send a transmission without coming up to the surface? What they could do is deploy a VLF, or very low frequency antenna. The reason is, a really low frequency can go through the water if the sub isn't too deep, without being absorbed by the water. However, the sub would not be able to use a typical radio frequency because that would be absorbed by the water. The issue of 5G's radio waves being so easily absorbed means that our existing cell tower infrastructure, it's not going to work. It's not going to be able to use 5G and give us that coverage we want. It wasn't a big issue to go from 3G to 4G because you could use the same towers. But with 5G, it's going to take more than just adding a 5G radio to an existing tower. Instead, we're going to have lots of base stations clustered tightly together. For example, in a large city, there might be 5G base stations mounted on street lamps or traffic lights. The good news is, once they are installed, these 5G base stations can support lots of simultaneous connections while giving us that incredible throughput. And 5G gets even better. In addition to having great throughput, it has really low latency. In other words, very little delay. Theoretically, that delay can be as small as 1 millisecond. Think about how valuable that could be for a self-driving car. Someone pulls out in front of you and your car needs to make a split-second decision. It's in times like that where milliseconds count. Next, let's consider Wi-Fi 6, which of course is referring to the sixth generation of Wi-Fi standards. These standards are set by the IEEE standards body. Specifically, 802.11n, that was the Wi-Fi 4 standard. 802.11ac, that was Wi-Fi 5, and now 802.11ax is called Wi-Fi 6. And Wi-Fi 6 was standardized in 2019. We talked earlier in this course about how two frequency bands that wireless networks use are the 2.4 and 5 gigahertz band. Well, Wi-Fi 6, it still supports both of those bands, and it gives us a theoretical throughput of 9.6 gigabits per second. Compare that to its predecessor, 802.11ac, which had a theoretical throughput of 3.5 gigabits per second, and that was a huge improvement over 802.11n that had a theoretical maximum throughput of only 150 megabits per second. Let's take a look at a few of the features that make Wi-Fi 6 so fast. One advantage of Wi-Fi 6 is that it allows us to represent more bits with a single waveform than previous Wi-Fi standards. It does that using a technology called 1024 QAM, which lets us represent 10 bits with a single waveform. Compare that to Wi-Fi 5, which let us represent 8 bits with a single waveform, and Wi-Fi 4, which only let us represent 6 bits with a single waveform. And also, a typical Wi-Fi channel spans 20 megahertz of frequencies. However, Wi-Fi 6 can logically bond together 8 of those 20 megahertz channels to give us a 160 megahertz channel width. That lets us have enough available frequencies to be communicating with lots of clients simultaneously. That was something that was also possible with Wi-Fi 5, but Wi-Fi 4, it maxed out at 40 megahertz channel widths. Wi-Fi 6 allows a wireless access point to have 8 simultaneous upstream and downstream connections with its clients. With Wi-Fi 5, we could only have 1 upstream conversation and 4 downstream conversations at any one time, while Wi-Fi 4, it didn't support multiple simultaneous conversations at all. And the transmission method is also different with Wi-Fi 6, and it's called Orthogonal Frequency Division Multiple Access, or OFDMA. That allows us to use a feature called Target Wake Time, which allows a wireless access point to tell a client when it's allowed to transmit and receive. That cuts down on the issue of having multiple clients contending for the same bandwidth at the same time. That's going to give us less latency. And also, since a client knows when it's going to be allowed to transmit and receive, it can put its radio into a low power mode the rest of the time. That's going to give us some power savings. It also supports Basic Service Set, or BSS coloring, which allows nearby access points to distinguish between wireless transmissions for different networks that are using the same frequency. So keep an eye out for 5G and Wi-Fi 6 technologies, each of which takes huge leaps in performance over their predecessor.